Bismillahirrahmanirrahim. In this video we will discuss the general method for sketching the root locus for a particular system. So the first rule when sketching the root locus is that the root locus is always symmetric about the real axis. The roots are either real or complex conjugate, right? So whenever the roots will be complex, they will exist as a complex conjugate pair. So there may be the complex conjugate roots, there may be the real roots, or maybe the combination of both. So the root locus will always be symmetric about the real axis. Whatever you will observe in the upper positive S plane, the same will be observed in the lower negative S plane, right? So the root locus in the upper S plane and in the lower S plane will be the mirror image of each other. So the root locus is always symmetric. Okay, that is the first rule. So if you get the root locus in the upper S plane, you can just take the mirror image of that to get the root locus in the negative lower S plane. Okay, so the second rule is now to find out the number of loci. So open loop transfer function poles, let's suppose those are equal to n, and the open loop transfer function has m number of zeros. So all the poles moves towards the zeros, and if the number of zeros are less than the number of poles, so then we say that those poles move toward the zero sitting somewhere at the infinity. So the number of total root locus will be equal to the number of poles, but out of that some poles will be moving toward the zeros, finite zeros, and some poles will be moving towards the infinite zeros. Pole always moves towards the zero. So if the number of poles are greater than the number of zeros, so the number of root loci, those are always equal to n, but out of those n minus m root locus will be towards the infinity, because the number of poles are n, number of zeros are m, number of poles are higher than the number of zeros, so then some poles will move towards the zeros sitting at the infinity. So each locus will start from the open loop pole and will end at the open loop 0. So the number of loci ending at infinity, this is that, so infinity, that is equal to n minus m, right? So imagine the zeros at the infinity. So total number of root locus or root loci will always be equal to the number of poles. So now let's discuss it with this example. Let's suppose that we have this open loop transfer function that is given by this expression. So the number of poles are over here, that is equal to 3, and there is only 1 0 over here. So total number of loci will be equal to 3, right? 3 loci, because we have the 3 poles. So one pole will be moving toward this 0, and rest of the 2 poles will be moving toward the infinity as the loop gain k is changed from 0 to the infinity. So in this we have 3 poles, pole at 0, pole at minus 1, pole at minus 4, and we have 1 0 at minus 2. So one pole out of these 3 will move toward that 0, and the other 2 poles will move towards the infinity, considering that their zeros are sitting at the infinity. The third rule for the root locus is to find out the which part of the real axis is the part of the root locus. So some of the loci will lie on the real axis. So a point on the real axis will be the part of the root locus if and only if the sum of the open loop transfer function poles and zeros to the right of the point is an odd number. So what that means, let's look at this example. Suppose we have this transfer function. In this we have 1 0 and 3 poles, and those are sketched over here. One pole over here, second pole over here, the third pole over here, and the 1 0 that is at s is equal to minus 2. Okay, so this is the real axis, all of these poles and zeros over the real axis, and this is the imaginary axis j omega. Okay, so now we put a test point over here, and if the number of poles and zeros on the right of that point are odd, then it means that point is the part of the root locus on the real axis. So for all the points from here to here you have one pole, so this is the part of the root locus. But if you take this portion of the root real axis, if you take a one test point over here, so if this is the test point, so you can see there are two poles on the right of this one, so this is not the part of root locus. So this portion of the real axis is not the part of root locus. Then if we take the test point over here on this portion of the real axis, so if you look at towards the right, you have 1, 2 and 3, 1, 0 and 2 poles, so total sum is 3, so that is an odd number, so this will be the part of the root locus. And if you consider some test points over here on this real axis, and if you look at towards the right of that one, so 1, 2, 3, 4, so that's an even number, so this is not the part of the root locus. So consider a test point over the real axis and then look at the total number of poles and zeros towards the right of that one. If that is equal to odd, so that will be the part of the root locus. That portion of the real axis will be the part of the root locus, otherwise it will not be the part of root locus. Okay, so these poles and zeros are shown over here. So this pole will move toward this 0, and these poles will move over this axis, and then they will depart from the real axis, right? So this real axis is the part of the root locus, right? Okay, so now let's move towards the rule number 4, that is that how we can find out the angle of asymptotes. So before discussing the angle of asymptotes, what do you mean by the asymptotes? Asymptote is basically the line along which the pole moves towards the infinity. As I told you that all the poles move towards the 0, so this pole is going to move towards this 0, but where are the zeros of these poles? The zeros of these poles are somewhere at infinity. This may move toward the negative infinity, and this may moves towards the positive infinity, so their zeros are sitting somewhere over there. So they will move at certain line towards the infinity, and those lines are said to be the asymptotes, right? And at which angle these roots will be moving, these poles will be moving toward the 0, basically they will move along the asymptote. So what is the angle of that asymptote with the real axis? Okay, so in this case I am assuming that it is the asymptote is at the 90 degree. Now let's see shortly that how we can calculate the exact angle at which these roots will be these poles will be moving towards the zeros. Okay, so now let's see the rule 4, how to calculate the angle of asymptotes. So if n is greater than m, right, so that is the number of poles are greater than the zeros, so n minus m branches will move towards the infinity, right? Over here you can see 3 poles, 1 0, so 2 poles are going to move towards n minus m. N is the number of poles and m is the number of zeros, so those will move towards the infinity. So n minus m branches will move towards the infinity, and these branches will move along a line which is called the asymptote. So asymptote is defined as a line on which the root locus touches the infinity, at which the poles moves towards the infinity, right? So these are just the rules which helps you to sketch the root locus. This is not going to give you the exact path. The asymptote is not going to give you the exact path, rather it is helping you to sketch by hand the root locus, that if the gain is changed, the open loop gain is changed, okay, then how the closed loop poles will change their position. So and a rough idea, a very close idea is given for about the root locus. Okay, so the number of asymptotes are equal to n minus m. So how we can calculate the angles for those asymptotes? Those are calculated with the help of this equation, that theta is equal to 2q plus 1 by n minus 1. So for that, for the positive gain, if the gain is positive, so what is q in this? 0 1 2 and so on up to n minus 1 m minus 1. So you will have to vary the q for up to this point, and starting from 0, so you can find out the angle of asymptotes. And if your gain is negative, then you will be using this expression, that theta is equal to 2q by n minus m into 180. So from what is q? Q is again varying from 0 1 2 and up to n minus m minus 1. Okay, so now let's look at the next rule, that is the calculation of the center of asymptotes. So what that means, the angle at which these asymptotes are going to touch the real axis, that is the angle of asymptote, and the point at which these asymptotes will meet at the real axis, that point is the centroid or the center of the asymptotes. Okay, so the fifth rule is for the calculation of that point. So the point where the asymptotes touches the real axis is called the centroid and will be represented by sigma c in this course, and is calculated using this expression, that sigma c, the centroid, is equal to the real parts of the poles of g of s into h of s, open loop transfer function, minus the real parts of the zeros of the open loop transfer function, divided by the number of root loci moving towards the infinity, n minus m. Okay, so now let's understand this one with the help of this example. Let's suppose that we have this open loop transfer function, right, and in this case greater than 0. So how many number of poles? 3 number of poles, 1 0. So n minus m, 2 poles will be moving towards infinity, and for the calculation of the angle of asymptotes, n minus m minus 1, that is equal to 1. So the value of q will be 0 and 1, right? As we have seen over here, the value of q varies from 0 to n minus m minus 1. So in this case, n minus m is equal to 1, so q will be having the value 0 and 1. Okay, so it means how many asymptotes? There will be 2 asymptotes, right? So now first of all, let's calculate the angle for first asymptote by taking q is equal to 0. So if the q is equal to 0, theta will be equal to 2q plus 1 divided by n minus 1, n minus m multiplied by 180. So this is going to give us 90 degree. Okay, and if the q is equal to 1, right, so taking this q is equal to 1, expression for the calculation of the angle of asymptote is this one. So we will get 2 into 1, 2 plus 1, 3 by 2, so that is equal to 270, right? And what is the centroid? The centroid is obtained by taking the real parts of the poles and the real parts of the zero. So what are the poles? First pole is at 0, the second pole is at minus 1, the third pole is at minus 4. All of these are real, right? So sum of these one will be equal to minus 5. These are the poles. And if we look at the zeros, so zeros, s is equal to minus 2, so real part is minus 2. So this is the sum of the poles, this is the 0, taking the difference of these two divided by the 2 asymptotes. So this will give you minus 1.5. okay, so now if I sketch the root locus for that one, when I will change the gain k, this k is changed from 0 to infinity, how the poles of the closed loop system will change their position. So that you can see over here in this diagram, that we have one pole at s is equal to minus 4, the other pole is at s is equal to 0, and the other pole is at s is equal to minus 1, and we have 1 0 at s is equal to minus 2, and this is the centroid, that is equal to 1.5 minus 1.5, that we have seen over here. This is centroid. So this is the point from where the roots will go into the asymptotes will touch the real axis, and the angle of the asymptote, the angle of first asymptote is 90 degree, that you can observe over here. This is 90 degree, and the angle of the second asymptote is 270 degrees. So this is 270 degrees. Second asymptote is going like this. Okay, now you can sketch the you can observe the root locus using the MATLAB. So if I define this transfer function using the MATLAB commands, so the MATLAB code is like that. The transfer function 1 and 2, this is the numerator, and these are the coefficients of the denominator. So if you multiply this one, so you will get an expression. So the coefficient of that expression is this one. So the root locus can be obtained either by the root locus command or by the root locus plot command. Okay, so you are taking this transfer function over here and you are sketching the root locus. So here you can say this is what we sketched, right? That our poles will be moving. This pole moving toward the zero, and these poles will be moving toward the infinity like this. One pole will be taking this path, first of all coming from here, sorry, coming up to this point and then moving toward that one, and this pole coming over here, let's suppose, and then going towards this infinity. Okay, so the root locus obtained from the MATLAB is shown over here. Here you can see these are the poles, right? So one pole is coming over here and moving, let's suppose this is moving over here and this is coming over here and then going to move over here. So this is the exact path of the closed loop poles. But if we talk about the asymptotes, asymptote we have drawn. So this is the line, so this is 90 degree, and this one over here is 270 degree, and this point is, you can see over here, minus 1.5. so asymptotes gives you the just idea that at which path your poles finally will be going towards the infinity. So asymptote at the, those are basically the lines at which your poles touches the infinity. Here you can see this pole, and similarly over here one pole will be moving and going towards the infinity like that. So it is just going to give you the idea, and this pole is moving toward this zero. So with the help of asymptotes and asymptotes angle, you can sketch that where your closed loop poles will be moving and they will reach towards the infinity zeros, the zeros which are sitting at the infinity. So these rules are helpful to sketch the root locus. These are not going to give you the exact, right? So for exact path you can use the MATLAB, and or you can change the value of the s, a test point. You can consider a test point and you can solve the transfer function to get the exact position from the angle and the position condition, magnitude condition, those we have discussed in the last video. Okay, so now let's look at another example. So g of s, h of s is equal to this transfer function. In this you can see there are two complex poles. One pole is this one, and the second pole is this one, and this is the complex one. The gain k is positive. One pole is sitting at the 0. So we want to sketch the root locus. So first of all, how many number of poles? 3 poles. There is no 0 over here that you can observe from here. So the number of loci is moving towards the infinity, that will be equal to 3. So n minus m minus 1 will be equal to 2, and that will be helpful for the asymptotes. So for asymptotes calculations, we will have to consider q is equal to 0, 1 and 2. So when the q is equal to 0, considering the expression for the asymptotic angle, so you will get 60 degree, one asymptote will be at 60 degree. When the q is equal to 1, your asymptote will be at the angle 180 degree. When the q is equal to 2, your asymptote will be at the angle 300 degree. Okay, and then the calculation of the centroid, the center point of your asymptote, the point at which your centroid will touch the real axis. Okay, so the real parts of the roots, real parts of the poles, for this it is 0, and the real part from here will be minus 1, and the real part from this pole will also be minus 1, so that is equal to minus 2. That is sorry, this is not sigma, this is the sum of the real parts of the poles. There is no 0, so now the sigma will be equal to minus 2 divided by n minus 1. N minus m is equal to 3, so minus 2 by 3, so the centroid will be minus 2 by 3, or minus 0.667. Okay, now let's sketch the root locus for this one. So here you can see the one pole is sitting at over here at the origin, and the other two poles are over here. One pole is this one, and the one pole is this one. Okay, so now if you look at the centroid, that is somewhere over here when the value of s is equal to minus 2 by 3, and there are 3 centroids. So sketching the first sorry, there are 3 asymptotes. One is this one, this is at the angle 60 degree. The other asymptote is at the angle of 180 degree, one pole moving towards the infinity at this path, and the other asymptote is this one. This is minus 60 degree, or in positive direction, in this direction it is 300 degree. Okay, so these are the asymptotes. So now how our poles will move along these asymptotes. So here you can see I have plotted it with the MATLAB. So MATLAB command is that one. First of all, I have generated a polynomial using the roots, the poles. First pole is at origin, the second pole is over here, and the third pole is over here. These are the roots. Using these roots, I have generated the polynomial, and then I have defined a transfer function with the command tf, right? So this is the numerator, that is 1, and the denominator is this polynomial. Okay, so now taking the root locus by using this command. So now if you look at this one, here you can see the poles over here are taking this path towards the infinity. Similarly over here taking the path towards the infinity, and this pole that was sitting at the origin is moving toward the infinity along this asymptote. So now compare it with this one that we sketched. So over here just observe that one, the pole at the origin that is moving at along this asymptote. Okay, so the pole that was over here, so it is going to take this path. It is like that, you can see over here, this is taking this path. So this pole will come over here and will take this path. Similarly this pole is going to take this path. Okay, that is the exact root locus. So with the help of the rules those we have discussed so far, you can sketch that at which path these poles will be moving toward. This is moving toward infinity, this pole is moving toward infinity, and this pole is moving toward infinity because there is no zero. All the zeros are sitting at the infinity, right? So now in the next video we will discuss few more rules with the help of which we can determine the angle at which these poles will be moving toward the infinity, right? And at what point these poles will cross the j omega axis. So we will discuss few rules in the next video. In this video we have discussed the 5 rules for sketching the root locus. The first rule is that your root locus is symmetric about the real axis, and then in the second rule there was the calculations for the number of poles, zeros and loci, and in the third rule we have seen that how we can check that which part of the real axis is the part of the root locus. The fourth rule is related to the angle of asymptotes. The fifth rule is the related to the center of the asymptotes, and then we have seen the examples to sketch the basic root locus. That's all from this video. In the next video we will discuss some more rules to sketch the root locus. Thank you very much.